Good evening. And welcome to the Newman Center. My name is Cecil Chabot. I'm the director here. And it's my privilege to welcome not just you who are here in this room, but those who are listening in on this event, which is being live streamed on the McGill YouTube channel as well. So we're here tonight for the 2018 edition of the Marguerite Juville Lecture in Science, Medicine, and Christianity. And I'd also like to extend a special welcome to Sister Elaine of the Grey Nuns, which were founded by Marguerite Juville. As many of you are aware, the Newman Center serves McGill's faculty and students as part of its chaplaincy services. But it has an equally important mission to support the mission and idea of the university itself, as inspired by John Henry Newman. As such, we aim to contribute to the intellectual life at the university as a whole in many ways, but especially by drawing on Catholic intellectual tradition in its diversity and depth, and engaging in conversation with a wide range of other traditions as well. To this end, we host 4 annual major public lectures, of which the Juville Lecture is the most recent edition, as well as other events and international conferences. In close affiliation with the Newman Institute of Catholic Studies, we publish the Newman Rambler and contribute to the Catholic Studies program at McGill. Now, this event would not be possible without the generous support of many people, and in particular our co-sponsors for this event this evening. So the McGill Center for Research on Religion, the Canadian Scientific and Christian Affiliation, the Newman Institute for Catholic Studies, the Newman Catholic Student Society, and also the Faculty of Science at McGill, who provided funds for Dr. Dominguez's trip. He also gave a lecture for the physics department last night. Now, there will be a question period after the talk, and there will be a small reception after that. Now, tonight's lecture asks the question, are science and religion compatible? The answers to this question vary tremendously, not just from one person to the next, but from one context and time period to the next. Peter Harrison, in his introduction to the Cambridge Companion to Science and Religion, writes, much recent writing by historians of science has addressed itself in various ways to the popular assumption that throughout history, science and religion have been engaged in a perennial battle. It is not generally accepted by historians that this erroneous view, known as the conflict myth, it is now generally accepted by historians that this erroneous view, known as the conflict myth, was largely the invention of 2 19th century controversialists, John Draper and Andrew Dickson White. Invention or not, the conflict model would not have endured had it not enjoyed at least a superficial plausibility, and if it did not play an important role in the self-understanding of those who perpetuate it. In fact, this model draws support from a number of sources: our present experience of religiously motivated anti-evolutionary sentiments and scientifically motivated atheism, well-known historical cases such as the Galileo affair that seem to exemplify conflict, the assumption that science and religion are forms of knowledge based upon mutually exclusive foundations, reason and experience in the case of science, and faith and authority in the case of religion. When examined closely, however, the historical record simply does not bear out this model of enduring conflict. Study of the historical relations between science and religion does not reveal any simple pattern at all. End quote. Similarly, in Science and Patristic and Medieval Christendom, David Lindbergh argues that the relationship is not one of warfare between science and church, nor is it a story of unremitting support and approval. Rather, what we find, as we ought to have suspected, is a relationship exhibiting all the variety and complexity with which we are familiar in other realms of human endeavor: conflict, compromise, accommodation, dialogue, alienation, the making of common cause, and the going of separate ways. And out of this complex interaction emerged the science and the religion of the Renaissance and early modern period, end quote. Tonight, we will hear a particle physicist give his answer to this question of the compatibility of science and religion. And I would now invite Professor Gerben Ugemal director of CREOR, to introduce our speaker, Dr. Aaron Dominguez.
Yes, good evening and welcome. My name is Gerben Oegema, director of the McGill Center for Research on Religion. We organize a whole range of different events and conferences: religious diversity in Quebec, indigenous traditions, religion and violence. And next week we have a panel on religion today, especially about religious and spiritual life of young people. CREOR, so is the keyword. But for now, it is my honor to introduce to you Professor and Dean Aaron Dominguez, who is the Dean of the School of Arts and Sciences and Ordinary Professor of Physics at the Catholic University of America. His main area of research is in using particle colliders to search for new physics, including the recently discovered Higgs boson. His area of expertise is in instrumentation, designing, building, and using silicon-charged particle trackers as precision tools to reconstruct the complicated interactions taking place in these collisions. He received his undergraduate degree from Whitman College and Caltech, his Ph.D. in physics from the University of California in San Diego, and was a postdoctoral researcher at Lawrence Berkeley National Laboratory. In 2005, he was the recipient of the NSF Career Award, played numerous leadership positions in the L3, CDF, and CMS particle physics experiments at the CERN laboratory in Switzerland. And from now on, I give up because there are too many abbreviations, but I'm sure he will explain it to us. At least the CERN, I know what it is about. But also equally important, as the Dean of the School of Arts and Sciences, Dr. Dominguez leads 18 departments and 7 interdisciplinary programs in the arts, humanities, and natural sciences at the university. He aims to change the course of students' lives and propel them toward a meaningful future. Dean Dominguez's mission, together with faculty, students, and staff from all faith backgrounds, is to raise the School of Arts and Sciences as a strong voice in the conscience of higher education. He is actively recruiting faculty and other leaders who will carry the research and Catholic mission forward together, building cutting-edge laboratories and facilities, and establishing institutions to serve humankind through Catholic social doctrine. Welcome with us, Professor Dominguez, and his lecture. Thank you.
Thank you, Ger, and thank you, Cecil, and thank you all for having me here. This is my first time to Quebec, my first time to Montreal. I've been to Canada a few times, but just pretty much out in BC. This is a place that I've always wanted to come, and I always had it in mind as this beautiful snowy place. So thanks for preparing it for me. I'm really happy to be here. I've really had a beautiful time in my 1.5 days here so far, and I'm looking forward to seeing the city tomorrow. This really is a beautiful place. This Newman Center is a beautiful place, and to see so many people coming out on a Friday night to the Newman Center to hear some nerdy professor talk about physics just fills my heart. So thanks for coming out tonight, and thanks from my bottom of my heart for hosting me here. So, as you heard, I'm the Dean of the School of Arts and Sciences at the Catholic University of America, which is located in the northeast quadrant of Washington, D.C. and the United States. We were founded in 1887 by the Catholic bishops of the United States with a mandate from Pope Leo XIII, who said, bishops, go out and form a university in the United States for the church. Go form a research university for the Catholic Church in America, and that's what they did. So we are founded by the bishops. We are the Bishops' Research University in the United States. We the only one that's like this, the only ecclesiastical or pontifical university, research university in the U.S. We're not part of a religious order or a diocese. We're the national church, the national research university for the Catholic Church in the United States. And personally, that's what drew me away from otherwise, which was a very beautiful and fulfilling job in life elsewhere, to come to such a place. And happily, I'm able to contribute and further this research mission. And I'd like to tell you a little bit about that tonight. So I'm a scientist. and I've always wanted to be a scientist ever since I was a little boy. I'm also a Catholic, lifelong Catholic, and I'm often surprised to be asked the question of whether or not it's possible to be a Catholic and a scientist, or even a believer of any kind and a good scientist. And of course, for me, the answer is obvious, and it's yes. But the fact that people are asking this question even today shows that I think that there really are still some profound misunderstandings about what it means to be a scientist, some profound misunderstandings of God and faith and the connection between these things. So especially in this time, especially living and working in Washington, D.C., where both faith and science seem to be simultaneously under attack, it's certainly an interesting time to be a Catholic physicist. So I am enjoying myself immensely. There's never a dull moment. And let me tell you a little bit about personally myself and how I came to be here. I do experimental particle physics. I'm extremely fortunate to work with my colleagues on the Large Hadron Collider, or the LHC, as we say, in Geneva, Switzerland. It's actually on the Franco-Swiss border. I'll show you a picture of it here in a moment. Our research group that I have at Catholic University and that I worked with before at my other universities, builds these particle detectors that are like super fast digital cameras that can take the picture of the radiation that comes from the collision of these proton beams 40 million times a second. And we use this accelerator, which is the largest machine ever built by mankind, to study the basic building blocks of matter. What are the basic constituents of the universe, and how do you put them together? In almost all ways, this is really one of our greatest technological achievements as mankind. And in almost all ways, I'm not one of these greatest men, but feel thankful to have been working with them over my career. I've spent my entire career in science, in academia, in universities, in laboratories, asking and working hard to answer these types of fundamental questions, which I'll show you a few of today. And this is something that I really have been working towards and wanted to do since I was a little boy. I always knew I wanted to be a scientist. I didn't know what a physicist was, but I did know that that's what I had always wanted to do. And I've been fortunate. It's not everybody has that experience in life, that you knew what you wanted to do when you could first speak and you were able to go off and do it. And it's largely through the support of people who loved me and have given me opportunities that I have been able to do this. And so my life has been marked by this journey to become a scientist, to be able to ask these types of profound questions. But my life has also been marked by my faith journey as a Catholic boy. And I was born and raised a Catholic in a Catholic family. And it was my maternal grandmother really who brought me into the faith, which is very common for Mexican boys like myself to have been kind of raised for the first part of their lives by their grandmothers. But she also gave me that allowed me to ask these questions about science. She, you know how grandmothers tell you these stories over and over and over in the family, and it's a way for them to remind you of who you are. And so one of the stories she would tell was when I was a little boy and I flipped on the light switch and asked how electricity works. No, I didn't. I asked how electricity works, and she went and flipped on the light switch and said, "This is how it works." And I said, "No, how does the electricity get in there?" And she said, "Oh, I'm in trouble now." And so it was these two things together, to being a Catholic boy and trying to become a scientist, that have always formed two parts of who I am, two halves of a whole. So I've never had this internal conflict that you might hear people talk about between their faith and science. For me, it's just been who I am, and it's been a part of what I do. So let me tell you a little bit about the kind of work that we do as physicists. Here Here's a aerial photograph of the region in Geneva, Switzerland, which shows an outline of the Large Hadron Collider, which is that big circle that crosses the Franco-Swiss border. Down on the lower right-hand corner, you see the little Swiss flag, and then a yellow line represents the Franco-Swiss border. The big lake over there is Lake Geneva, and the bit on the left is France. And so you can see this is an enormous complex. The Geneva airport, you can see just on the right-hand periphery of the picture, you can see in proportion to the accelerator laboratory that it's much smaller than this ring. What we do with this accelerator is to take protons, which are the nuclei of hydrogen atoms. So you take literally a bottle of hydrogen and use an electric field to strip off the electrons so that you just have protons, and then collect those and accelerate them in opposite directions in two different beam pipes. And in these two different vacuum beam pipes, they travel in opposite directions at nearly the speed of light and then collide at the 4 points around the ring, which have those acronyms, CMS, ALICE, ATLAS, and LHCb. Sorry, sometimes I see this in French, then it gets stuck in my ear. They speak French over there. So the beams collide at these 4 experiments so that we can create these types of collisions, which I'll show you, that allow us to peer and peel back the layers of the universe to look at what are the kernels, what are the most fundamental building blocks of nature. And in order to accelerate them to these extremely high energies to produce enough energy to peel back these layers of the universe, we have to use extremely powerful magnets. And in order to do that, we have to use superconducting magnets. And at least today, to make this type of very powerful superconducting magnet, you have to cool it down to these cryogenic temperatures using supercooled liquid helium. And so in fact, the magnets and the RF cavities that we use in the accelerator down there are at negative 271.3 degrees Celsius, or just 1.3 degrees above absolute zero, which is colder even than outer space, believe it or not. Outer space is closer to 3 or 3.5 degrees Celsius. So we have not only the biggest scientific instrument in the world, but the coldest biggest at least. So this is the largest cryogenic mass on the planet. Who knows, maybe in the universe, unless there's some aliens out there that have built their own LHC. And the tunnel, which you'll see that contains the beam pipes and the liquid helium and distribution, power, cooling, all the data cables and whatnot, is located about 100 meters underground. So that trace of the circle that you see in the aerial photograph, you can't really see that from an airplane, because all of the stuff is underground in a big tunnel that looks like a subway tunnel. So it's located underground, quite deep actually, 100 meters to 150 meters, depending on where you are in the sort of the plains, the Geneva plains that go from the Jura Mountains down to the lake, for 2 reasons. One, to shield people and other things from the radiation that comes from the collisions, but mainly we could actually accomplish that much easier with just a little amount of earth. Mainly it's down this deep because that's where sort of the stable solid bedrock is in Geneva, which is the leftover of a giant glacier that went through there and left a bunch of rubble. So you have to go down that far to kind of find the bedrock there in that Swiss plain. So that's why it's so deep. It presents some interesting challenges to try to put a whole bunch of stuff deep underground and to work there. And you can see in this picture that there's not a whole lot of space in that tunnel. A person is about as tall as where that yellow klaxon, that yellow light is. So there's not a whole lot of room in there. And you can see it bending off into the distance. This circle that we see in the aerial photograph is about nearly 30 kilometers around in circumference. So if you were to run around the ring, you would have run 30 kilometers. And so my experiment is the one that was labeled CMS. It stands for the compact muon solenoid experiment. It's the one that's sort of the furthest away from my office inconveniently. So I have to drive clear across the French countryside to get to the experiment. The guys who work at Atlas, that's the closest one to my office, and those are my competitors. So they outsmarted me. So our experiment, so there were two other experiments which were smaller and more specialized, which I won't talk too much about tonight. I'll talk about this CMS experiment and this Atlas experiment, which are doing more or less the same thing as two competing experiments to check each other's results. So this CMS experiment, and Atlas even more so, is huge. It's the size of a 4 or 5 story building. It's the size of a church, the size of a small cathedral. And it's located 150 meters underground in this gigantic cavern. And I can tell you, working there, it's almost unbelievable. It's like being on the set of some science fiction movie, except that it's real. We are really doing this. This is a real thing that we're doing. And it's almost unbelievable. It never gets old to go down there and work on this stuff. So I'm always filled with awe and wonder, even if it's something that I'm doing every day. When the proton beams collide at these extremely high energies, they make effectively a tiny nuclear explosion. In terms of the total energy released, it's very small. It's about the total energy is about the energy contained in a bumblebee flying around. So if a bumblebee smacked into you, it wouldn't cause you, it wouldn't like kick you across the room. So it's a small amount of total energy that's released when these things collide, but it's very compact. It's very localized in a very, very small space. So the total energy there's no danger of blowing up Switzerland or anything. So just in case, this was something we have to convince people of periodically. There's no danger of doing that. But the point is that we have squeezed down this energy that's contained in, say, like a bumblebee or a fly, down into something that's smaller than a proton, smaller than the constituent of the nucleus of an atom. And that's what's so interesting. In fact, we're able to reproduce the energies of particles in this collision that were present on average in the very early universe just moments after it was created in the Big Bang. So we are literally able to recreate the average energies of the stuff that then become all of us, everything in the entire universe, a trillionth of a second after creation. And that's what we do 40 million times a second. So the reason we're doing this is so that we can study the following things. What are the basic building blocks of the universe? What are the rules for putting these building blocks together? How does the universe work, and how has it changed over time and evolved since its initial inception to its current state today, and eventually what will be its future state long in the future? So those are big questions. Here's a photograph of our CMS experiment to give you an idea of what it looks like and how big it is. You can see down on the floor there, one of our technicians wearing a yellow hard hat. So he's only about yay big, and that experiment goes all the way up 4 stories. And right now it's in the open position. The beam pipe, the beam that contains the protons going in opposite directions, the pipe that contains the protons going in opposite directions would go right through the heart, right through the very middle of this experiment. We have it in this open position so that we can work on it, check it and fix anything that's broken. And then we actually close it up when it's time to run. Here's a photograph of our folks who helped us build and install the detector that we worked on, that my university groups have worked on. And you can see what it's like to be working at heights. You have to be wearing safety equipment. That yellow platform is a temporary scaffolding that you're up there with this thing that's being lowered down by this giant overhead crane. To get it down there, it had to be lowered down a big borehole from the surface. This is 150 meters down. Brought to the floor of the cavern and then picked up by another crane and brought over there and put on this platform and installed with the precision of microns. So here's a cool animation that one of our students made of what one of these collisions can be visualized as using reconstructing the information that comes from our detectors and putting it into a form that our brain, that our mind can comprehend with sort of a simple picture. So I'll press play. And you can see these blue blobs represent the two beams coming in opposite directions and colliding right at the heart of the experiment. When they do, it makes this explosion of other particles. And the different colors represent different kinds of particles going in different directions. And the size and shape represent the energies or speeds of these different types of particles. And the paths represent where they went. And so we do that over and over and over with our detectors that you saw in the photographs. And I'll show you how they work briefly as well. To build up a statistical picture over and over of the kind of physics that we're interested in studying. So here's one freeze frame of one of these collisions. This is one that's compatible with the discovery of this Higgs boson in 2012. And it represents just one event. We collect about 40 trillion of these events in the course of a year when the detector and the experiment are running. And the reason we need so many events, like, okay, here you've got one, why do you need 40 trillion? Aren't you satisfied with just one? Well, the problem is that to find just the one, we need 40 trillion because we don't actually produce 40 trillion of the events we're interested in. We just produce 1,000 or 10,000 of the events we're interested in, buried inside of this other very large population of events, which are interesting in different ways, but not probably what we're looking for, and represent some type of a background to the processes that we are interested in. So we're interested in very, very rare processes, and that's why we have to produce so much data and have accelerators that collide so often, so frequently. So here's a cartoon, a blown up cartoon of our experiment, and you can see the different components of it and what they do. On the left, you see the silicon tracker, which is what we were installing in that photograph on that yellow platform. And it's right at the very heart of the experiment. As you could see in the photograph, we were installing it right in the very center of this very large experiment. And its job is to measure the paths of these charged particles, where they went. We can reconstruct where they went and how fast they were going or what their momentum was. The crystal calorimeter and the Hadron calorimeter are used for measuring the energies of particles that interact with the electromagnetic force. So like very energetic photons, for example. Like if this projector were a source of extremely high energy photons like gamma rays or X-rays, we'd be able to see the energy, measure the total energy of those particles with this crystal calorimeter. In the Hadron calorimeter, we're able to do something similar with things that interact with the strong force, like protons or neutrons, the stuff that make up the nuclei of the atoms that you and I are made of. At high energies, they make it out to the Hadron calorimeter, and we measured their energies there. The muon chambers, the things on the outside, measure the momentum and paths of these exotic particles called muons, which are heavy sister particles to the electron. And so this octant slice of the experiment kind of shows you that visually, that each of these different types of particles, which are listed out there, muons in blue, electrons in red, charged hadrons like a proton or pion in green, the dashed green line, a neutral hadron like a neutron, or the dashed blue line, a photon, each leave a different signature in our experiment. They all look, you can tell with your eye that there's a different pattern for each of those particles. And so each of these detectors is responsible for being sensitive to a different form of radiation coming from this complicated event. So it peels apart what's happening in that one collision, and each of these different detectors is responsible for a piece of the puzzle that we put together from these different pieces and make this one complete image of one of these events. So this represents just one of these events that happened 40 million times a second, and so these detectors are like a super fast digital camera that's strobing and taking a three-dimensional movie of what's going on every 25 nanoseconds. So, as you can see from the photos of the scientific apparatus and the accelerator itself, it's huge. I mean, it's giant. It's the largest scientific instrument ever built, right? It represents a huge scientific endeavor, maybe the biggest one that we've ever done so far. And it literally requires the cooperation of thousands and thousands of scientists from around the world. In this picture, you can see a little pin that's placed for every collaborating institution that works with me on the CMS experiment. You might see an important country that we're sitting in right now that's missing, and that's because they've all banded together to be on the other experiment that competes against me. But you can see from the worldwide, and if I were to show you a similar picture of the Atlas collaboration, it would be covering the rest of the world that's not there for the most part. And in fact it's a larger collaboration than the CMS collaboration. So it really is a worldwide endeavor. Each of those pins represents a university, an institution, a laboratory, some kind of research group. So those are the smartest guys in the world, all working together on this one project. And now we're working on two competing projects, but really I'll tell you a bit about how we do it. And it's quite a beautiful thing. And in that picture that you saw of us installing our tracking detector on that platform, my colleagues that helped us build and install this detector on that platform, when we were doing it, when I was there, we were speaking French, we were speaking English, we were speaking German, we were speaking Swiss German, we were speaking Italian. There were guys down there speaking Russian. And so it really was a global effort, in a very real way, a very personal way, to get this done. It also reminded me why, when I was growing up, I should have learned French. I grew up in the southwestern part of the United States, where Spanish is the language of many people there, including my family. So I thought, well, I can get by with Spanish when I show up in France in the early 1990s, and I learned French the hard way. But now I speak okay French, thanks to the douanier. So here's another view of this the CMS collaboration. 2,885 physicists, 922 Ph.D. students, 995 engineers, 279 technicians, 198 different institutions, so universities, laboratories, etc., 45 different countries or regions. We have about 5,000 people, over 5,000 people actively working together on this CMS experiment. So why do we need so many people to do this? People like to do their own thing, especially scientists, right? We all have a pretty high opinion of ourselves. And so why would you possibly imagine it would be a good idea to get 5,000 of us together to try to work on something? So why would we ever contemplate trying to do what seems to be much harder than the actual science that we learn, at least in school? And it's because it would be impossible for one man or for one woman to do this on hers or her own. It would take thousands of years for one person to do this. It would be impossible, right? So we do this because we all share the same goal. We're all interested in trying to answer these same questions. We're trying to understand what the world is made of and how it works. And everyone in that picture, in that map, we're working together voluntarily. There's nobody forcing us to do this. Okay, there's no dictators that say you have to go and be a physicist and work on this experiment. We're all doing it of our own free will. It's literally a global and cooperative effort. And if I can talk a bit about today's mass readings, in the first reading from the first book of Kings, we heard about the separation, the disillusion of the people of Israel being torn apart because of our own sins, because that we couldn't get along with each other. We fell away from God, and now we've been kind of torn asunder. And in the gospel reading, we heard Jesus healing a man who couldn't hear and couldn't speak. And Father, if I can embarrass him, gave a great homily that pointed out that we should be, in this time of division, we should be opening our ears to each other, and we should be speaking kindly to each other with charity in our hearts. And so for me, I'm proud of the science that we've accomplished, but I think probably our greatest achievement is that we've proven that we can work together on something like this peacefully. So for me, this kind of example gives me hope. This is an example of people from all different backgrounds, from all different countries, some of which are enemies. We have Turks and Greeks working together on our experiment. We have Iranians and Americans working together on our experiment. And we're all working together because we share this common goal. So for me, that's one of the most beautiful things that we've accomplished. And you don't hear people talk too much about that aspect of the science. So what have we learned? Well, we've learned that many of the basic building blocks of nature, what they are, and we've learned what some of the fundamental forces are and how they interact. And this little periodic table that you might see these days in your physics textbooks if you're in high school or college represent what we've learned so far. You've also learned that physicists have really bad senses of humor when it comes to naming particles. Like we've got the up quark, the down quark. Okay, that makes sense because one's on top and one's on the bottom. But then we've got the charm quark and the strange quark, and well, the top quark and the bottom quark because we already used up and down. So, and this periodic table represents all of the particles that we've been able to directly create and observe in our experiments, and really represents the work of literally of thousands of people. So this is a profound. Represents a lot of work and a lot of profound discoveries of what the world's made of. So we've understood better the matter that makes up me and you and how things work. Electrons and down quarks and up quarks, for example, are what make up all of the atoms of our body. But we've also discovered there's these other things. That's why we call them strange and stuff like that, because we didn't really expect to find an extra copy of the same type of matter that makes up me and you. And in fact, we found that there are 3 copies of such matter. There are these 2 other generations of matter besides the stuff that makes up me and you, and we don't really know why. We know they certainly exist. We know they exist because we're able to produce them directly in our particle experiments. And therefore we know that they were present in the early universe, but now they're basically extinct. They don't exist. There's no charmed strange quark people, right? They're just made of up and down quarks now. So They were also present, however, in the very early universe, and this is some kind of clue that's telling us this is a profound clue of how the universe is put together, and we haven't quite understood what it all means, but it definitely must have had an impact on how the universe evolved after its initial creation into the state that we see today. In 2012, we discovered the little box up there on the right called the Higgs boson, and this led to a Nobel Prize for the physicist who had originally proposed it in the late 1960s. This Higgs boson is responsible for giving the masses to these other particles. In other words, it determines how heavy they are. And it's strange. We don't totally understand what this Higgs boson is. And in fact, you think, okay, it gives it mass. It must be gravity. But actually, it's distinct from gravity. As far as we know, it's not gravity. Gravity is the force that pulls matter particles together that do have mass. But the Higgs boson doesn't have anything to do with gravity. So there's certainly a big mystery left to solve involving how gravity works. And if it weren't for this Higgs boson, then the particles on that table would all be massless, and therefore the stuff that would potentially make up me and you would also be massless. And the problem with that is that Einstein's theory of relativity tells us that if something's massless, it's traveling at the speed of light. So the stuff that would potentially be making up me and you would all be traveling at the speed of light in different directions, and it would be impossible to form us, be impossible to form these types of, it would be impossible to form stars. They wouldn't coalesce together without mass. So no stable forms of matter would exist like atoms. Without atoms, we wouldn't be here, we wouldn't exist, there'd be no Earth, galaxies, etc. So it really is kind of an important discovery. Apart from the types of experiments that led to this little periodic table, we also discovered that the universe was created about 13.8 billion years ago out of nothing. There was nothing before this. It wasn't like cold, empty space with a pile of stuff that blew up for some reason. There was no space, there was no stuff, there was no time. There was literally nothing before it. We've also discovered that the heavier elements that make up me and you, like the iron in our blood, the silicon in the ground that makes up glass and dirt, came from supernovas, came from the death of heavy stars. And that's what cooked up the elements that make up me and you. So we've learned the physical rules that govern this natural world and how strange and huge it is. From its inception in the Big Bang, really, to its current state, there's lots of stuff that we don't know. This is an exciting time to be a scientist because there are really some big questions out there to fill in the gaps between the beginning of time and now. But we have learned, without a doubt, that you and I are sitting here having this discussion because of the way the universe has been created, because of the way it's evolved, because of the rules and the interactions of matter that you see on this table, because stars have had supernovas. So we are literally self-aware parts of creation. We can think, we can study ourselves, we can study creation itself, and we can ask these types of profound questions. And this is what science can do. This is what science can tell us. It's an amazing achievement of mankind, right? But in fact, this is all science can tell us. This is the limit. This is as far as it goes. Science can do no more than that. It can't tell us why this has happened, or what it's for, or what it means. Science can't know itself. That's the limit of what science is. But clearly that's not who we are as people. We want to know the answer to these other questions too. It's built into who we are. So what does this mean? Here we are, self-aware pieces of creation, living in this world that's clearly intelligible. In other words, we can carry out these experiments and understand this order that's out there in the universe that we're not responsible for. It's there, and we can make sense of it. We're driven to understand this world that we live in. But we're also driven to search for meaning and to search for God. And this search for understanding is clearly built into who we are as people. Our search to know God, His revelation to us, our understanding of who we are and what we're for, that's what helps us make sense of all of this. It helps make sense of this amazing natural world, and it's what allows us to give meaning to these discoveries. Science can't do that. And this is where faith comes in. In fact, for me, without faith, science becomes incomplete and even a failure. Science and faith are not incompatible with each other. They're two halves of a whole, of seeing the world, the universe, as it is. Science can't scientifically disprove that God exists, nor can it scientifically prove that God does exist. But as I said, science can't know itself either. Its principles, in fact, have to be assumed. You have to take an article of faith to believe that science itself works. Science itself doesn't prove that it works. You have to believe that it does. So our science has uncovered the truth that the universe was created out of nothing, and from this creation came all of the rules of physics that we've been able to uncover, including all of the creatures and wonders, including me and you. And as people of faith, we've learned through divine revelation why this has happened, and in fact, it's perfectly compatible with these scientific discoveries that I've outlined for you tonight. God is the creator of the universe. He didn't create himself, and he's existed even before time itself. Those three statements are all compatible with these observations that we've made scientifically. And he's created this world so that we would exist, to understand it and ourselves and him. So I think, in fact, we can take that line of approach with everything that we do in life, with everything that we do in a university, not just in physics or the hard sciences. We can do this in every profession. And this, in fact, is what we're trying to do at my university, at the Catholic University of America, where we're free not only to study the physics in our physics classes, to learn our disciplines, but to ask these types of questions. What's the meaning of this? How do we do this science the right way? What's good about this, or what's bad about this? What's the truth? Where to look for beauty? Where to look for transcendence? How to understand our relationship to each other, to the natural world, and to God. Not only is it possible to be a man of faith and a scientist, it's the only way to be a complete scientist. And for me, it would be like looking at the world by covering one eye if I didn't do both. So here's just a concrete example of this from a very, very recent, just in the past month, scientific discovery. What you see there in the center is an artist's rendition of the collision of two neutron stars that we were able for the first time to observe directly using multiple scientific instruments, which are outlined down there in that little world map in the bottom left-hand corner. We used gravitational wave detectors, where the little yellow dots are, that are spread around the world, one in Europe and two in the United States, and a collection of ground-based and space-based telescopes with the blue dots to observe this one event, this one cataclysmic event of the collision of two neutron stars for the first time using both of these techniques. So it's the first time we're using gravitational waves to do astronomy, and it really represents a giant leap forward for the way that we can understand the world. So what do we learn from this collision between these two neutron stars? Well, we discovered where the majority of the heavier elements like gold come from, and platinum. The supernovas that I mentioned before don't produce enough gold to represent the amount of gold that we see when we dig stuff up. There must have been some other mechanism to produce gold. And it turns out that the gold that makes up our wedding rings that we give to each other to mark a life together come from the collision of supernovas. And if that's not beautiful, if that doesn't have some amount of transcendence in it, I don't know what does. So, reconnecting faith and science. I think if we don't do science this way, we leave our faith out of it like much of the culture is pressing us to do and, in fact, discourages us from doing. Then we put ourselves at risk. We put our planet at risk. We put our species at risk, and we put our souls at risk. And this one example, we've joined together in our common humanity as scientists to work together across the world on these big scientific problems because it's in us. It's what we want to do. It's how we've been created, precisely because this is the way God has made us. This is a fundamental connection between faith and science. And I think we should use our souls, where God lives within us, as a kind of a mirror to reflect with humility upon these scientific discoveries and ask these questions. How do these endeavors affect our souls? Are they leading us towards God? For me, this is the connection between spirituality and science. And if people attack your faith with science itself, I think you can remind them that, in fact, the church invented the scientific method. In this picture below here, you see the view from my office at Catholic University of America of the Basilica of the National Shrine of the Immaculate Conception of the Blessed Virgin Mary. It's just breathtaking. It's beautiful. And in the east transept of that basilica, there's a mosaic of the creation story. You see the hand of God reaching down, creating man and the cosmos. If you're there up close, you can see images in the mosaic of atoms, of the DNA molecule, of dinosaurs, of all the animals that are present and have lived in the past, and represents the story of the kind of stuff that we've been studying as scientists. And it's right there in our nation's basilica in Washington, D.C. So, as a physicist, without God, I don't think I would be whole, and my search for these types of scientific truths wouldn't have meaning. And that's what gives me hope every day, is to get up and to be able to do that, to work at a university where I'm not only encouraged to do that, but to make it possible for others as well. So thank you very much, and God bless you. So, go ahead. Questions?
Yes, we'll open the floor for questions. And before we do that, I just wanted to share with you a couple of quotes or paraphrases, because I can't quite remember the quotes that came to mind during the talk. First, God is the one who makes things in the world because there can't be nothing all day. That came out of the mouth of my 2.5-year-old daughter quite some years ago. She's 10 now. The second, religion is that sense of amazement before the mystery of reason incarnate in existence, the depths of which we will never plumb. That was Einstein. And the gap between what my 2-year-old understood and what Einstein understood, I think, is insignificant compared to the gap of our current scientific knowledge and the depths of what is knowable. So, with that comment, I open the floor to questions.
Thank you, Cecil. So if you have a question, there's a microphone right there in the center of the room. And if you go to that, then everybody will be able to hear it. This is actually on the internet, which scares me to death, but it's on the internet, and they'll be able to hear you if you use the microphone. Yes. Come on down.
Hi.
Yep, good.
There's this argument that Brian Greene has about miracles. I'm not sure if you're aware of it.
I don't know exactly what his argument is for or
So
against.
basically the idea is that a miracle is a low energy, would constitute a low energy interaction with something, right? Like it would have to communicate with this world in some sort of low energy way. And that by like CPT symmetry, basically you should be able to reverse it and do some sort of collision that would go into the process that the miracle came from.
So an
and that in the absence
anti-miracle.
of seeing that, you can infer that there are no miracles at the energy scales that we see.
Well, I would have to read his argument. Brian Greene is a brilliant, physicist. He's probably not a brilliant theologian in the same level. I don't know. Maybe he is. I don't know the man personally. But I do know that those types of arguments and scientific proofs of miracles, in this case, it sounds like trying to produce an anti-miracle that would, annihilate a miracle.
It's a time reverse or momentum reverse of a miracle. Yeah.
Right. Yeah, I mean that just those are just not two things that you can meaningfully talk to together in the same breath. It just doesn't work to try to prove or disprove God using science. That's the boundary. And with that, I hope there's more questions. Yeah. Yeah, sure. We got a fellow at the microphone there, and if you've got a question, you can go back there, and you can be next. So please.
Okay, I wonder if you could say something about the relationship between truth and science, where the boundaries are there. And as far, it seems like if truth is immutable, science really isn't immutable in the same way. But the perception, at least in Western society, is kind of flipped on that. And I don't know.
Yeah, so there is truth with a capital T, and certainly as believers we know that there is such an underpinning of philosophical foundation to the world that there is truth. There are things which are true and which are not true. And in science we do uncover truths. I mean, there are scientific truths. Science is a human endeavor, and so therefore it's not perfect. And sometimes we find things that we didn't expect and overturn what we thought used to be true, but it doesn't mean that there aren't some true, actual scientific truths. They exist. Just like there are other truths about God. And these two things are not incompatible. If something is true, it's true. If two things are true, they're both true. One truth does not negate another truth. That in fact is the logical beauty of our faith.
Thanks for your talk tonight. Could you make some remarks on in your discipline of creativity and the aspect of discovering new theory and coming up and furthering a field in your specific discipline and using our gifts of reasoning and of intuition to apply them creatively into scientific research?
Thank you. Yeah, it's especially now that I'm the dean of a School of Arts and Sciences, and I get to see how artists work and how historians work and how poets work, and I know how physicists work. I see that this creative process is very similar. The act of creation, the act of having this imagination, is very similar across these disciplines, and I guess it's not surprising because we're all people, and in fact that's how we work as people. And so yeah, in order to conceive of this gigantic idea, this gigantic project was a profoundly creative act. And every day in the lab, I guess you spend most of your time trying to fix stuff that doesn't work, and trying to understand why it's broken. But in order to do that, it requires not just persistence, but creativity. It requires an imagination, and that's really the fun part. So for me, it's kind of what gives you joy, is being able to use your creativity to imagine and solve these types of problems. And I find that actually to be very common across all of the disciplines, not just in the sciences, but in the arts and the humanities too. Yes?
Yes, A few years ago, everybody was trembling. They were afraid that there was an experiment going on there
Yeah,
that would create a particle that would swallow the whole world in.
right. Yeah,
And
even,
can you talk about that a bit?
yeah, in fact, there was a man who sued all of the physicists in the world. I'm not making that up, and he's probably watching us on YouTube. No, we were almost certainly completely. It would have been impossible for us to destroy the world by turning on our accelerator, and in fact, we achieved it at breaking our accelerator, not the world, and we had to fix the accelerator. But maybe what this comes from is a misconception of black holes. It is true that we could be producing microscopic black holes in these collisions that you saw these images of, and it's something that we're searching actively for. We're actually trying to see if we are producing microscopic black holes in these collisions. But they're of such minuscule mass that they wouldn't swallow anything. In fact, Hawking has told us that they evaporate, and that's what we would be looking for, is the evaporation, the quick evaporation or disintegration of these microscopic black holes. And that's because gravity is so incredibly weak. And I'll show you a demonstration of how weak it is. Here's a pen that I'm holding in my hand, and I've just defeated the entire gravitational pull of the whole planet Earth. Right? And this pen is made up of 10 to the 23 atoms, right? And we're producing a black hole, which would be, 1 part in 10 to the 23 of such a thing. And so it would be incredibly weak, right? And that, in fact, is a mystery, is why is gravity so weak? But no, thankfully, we do stupid things as physicists sometimes, but we at least planned ahead, and we're not going to destroy the world with when we turned our experiment on.
Was that the same as the God particle?
The God particle, which is a horrible name, I don't like it much. And in fact, there's a story of why it's called that, which I can't talk about in a friendly audience with children present. But that's this Higgs boson, which we saw in this periodic table. And it was a sensational name that was given to the particle by a journalist and not by a physicist. But yeah, that's the Higgs boson, is the thing that's responsible for giving masses to the other particles. Yes. Okay, thank you.
Can the existence and transcendence of the soul may be a proof that there is higher dimension than space and time and matter and energy?
Yeah, so there's the existence of the soul, which is, a separate reality from the physical world. Well, it tells us that there is a spiritual world, and that there is something that is outside of the physical world. I think that is what it tells us. This is an article of faith, that there is a soul. But I think from our own experience, just looking deep inside of who we are, I think we can see the existence of our own souls, and people have discovered that many times over the ages, not just as Christians.
You are talking about faith, about souls. My wife is a nurse, and we have been together for the last 38 years. She saw so many people dying and coming back, and strange vision in their eyes.
Yeah.
It's not just a kind of a philosophy. There is something that our brain don't understand yet.
Absolutely, I agree. And I think if we open our hearts and our minds to God like this, then we can see these things. And that's what he's telling us to do. Yes?
I just want to thank you again for coming and joining us here in Montreal.
Thank you.
Wonderful talk. I'm a surgeon, and so I use hopefully very sound scientific principles. I also am engaged in research, but ultimately it's a human endeavor. And there was just an experience yesterday that sort of brought this talk that was coming up to mind. We were operating on a very difficult case, maybe who'd been operated several times before. And the parents are very devout, and they had the Pope's picture that they wanted, Pope John Paul. They wanted the picture next to the baby during surgery. And there was also a family just next door to them in the neonatal intensive care unit that were very strong believers in a Lebanese saint. And so they've asked if they could also have the picture of that saint with the baby. And so they had both of them next to the baby's head as we were operating. And, people, of course, tolerated it, no problem. But the comments that were coming from the anesthesiologists and some of the others in the room was this you could tell that there was a lot of discomfort. Things like, maybe we should cut them into small pieces and put them next to the esophagus, might heal better, that kind of thing.
Yeah.
And I, every second week we have a fetal conference where we discuss fetal conditions. And of course, in Canada, abortion on demand is present at any time during gestation from day 1 to week 40 if needed. And so there's always a lot of ethical discussions. And what is interesting is on many occasions over the course of years, there are parents who've chosen not to terminate pregnancies despite very strong recommendations from physicians to do so, and babies are born normal. Mm-hmm. And what's interesting to me is that there are no lessons learned. In other words, it's often this flippancy used, like, okay, maybe we should have them pray for other patients, or that kind of thing. Like, there's really no sense of humility. So my question is, we're often told that faith is afraid of science because maybe it challenges the pillars of faith. But in your experience, is science afraid of faith? Because in my experience, I find it very much so.
For me, science, and I think what I was trying to show, leads me personally closer to God. And I think actually we can use science as a tool of evangelization instead of what it's being used for now, which is what you're saying. People are being beat over the head with science to get away from God. But it doesn't make sense. It doesn't make sense if you, unless you're being kind of pushed in that way. It just doesn't add up to me that these two things are incompatible. And yeah, there's lots of cynicism out there and pessimism, and those people, they do it for various reasons. Many of them because they feel uncomfortable with their own struggles internally. That's the charitable way to say it. The other is that they are really not our friends. But in fact, we have to meet these people where they're at and bring our own witness to them with humility instead of with the pride that they're bringing towards us. And that's a hard thing to do, but that is in fact what we're being called to do. But literally, the beauty and transcendence of the understanding of the universe, of how the human body works, it's just such a profoundly beautiful thing that it speaks to the type of beauty that comes from God.
Hi, thank you so much for your talk. In your talk, you used the word mankind a few times, and I just wanted to tell you that here in Canada, we have a different way of anyways. But my question was, in the discovery of these new quarks, I was wondering whether those discoveries have any potential impact on how we understand human DNA.
That's a good question. I don't know the answer to that. I think probably not. DNA is mainly the result of chemistry, which is a much lower energy type of interaction than these that's present to be able to create these other quarks, which are all of these other quarks that you saw, and these heavier forms of copies of the stuff that make up me and you are unstable and decay rather quickly, much more quickly than the time scale involved in chemical interactions. And so they, at least at the level of chemistry, they don't seem to have much, if any, impact. So I don't know the answer, but I would suspect that it's probably not, doesn't play much of a role in how DNA works or came into existence. But there's lots we don't know about the evolutionary microbiology that led to DNA as being so ubiquitous across all of life. So it could be that there's some symmetry of nature that comes from part of this that is leading this to be the solution that leads to life. That I don't know. Yeah.
Can you give us some recommendations for books on faith and science that you've read that have intellectually formed you that you'd recommend?
Well, we were talking just briefly over cookies and tea before this. Father Robert Spitzer, has done a lot of this with the Magis Institute, and there's a lot of his materials available online as online books and videos, and there's lots of contributions also from other scientists. So I would actually start there, and that's a free resource. If you just Google Father Robert Spitzer, you'll see a lot of that. He's a brilliant man. He's a priest and a philosopher and a scientist. So I would definitely recommend starting with that.
Hi, thank you for your time. I just had a quick question. There seems to be an underlying tone in my personal experience around the university that intelligence and faith, they're not compatible. And so if you're smart, or if you're amongst the smart, then you're an atheist. Or I guess for those who are super intelligent and do believe, to them, they portray it as almost a laziness of, oh, we don't know the answer, so we're just going to brush it off and label that as a product of God. You as one of the most intelligent people in the physics community, and definitely surrounded around a lot of intelligent people, is that the same kind of environment that's in kind of the upper, I guess, the limits of science, where people are pushing the limits of science and discovering more every day?
Well, look, we all learn more and more the older we get, and I think we learn that we know less and less. Certainly, what you're talking about is a form of pride, and I think we've learned nothing. If nothing, pride is something that leads us away from true understanding. So I would point that out to them. The other is that, I've spent my whole career mainly in secular institutions. It's only recently that I've come to Catholic University of America. I spent my career in other very just excellent places that are not founded on, the Catholic faith or the Christian faith or anything like that. But they're filled with good people. They're filled with my friends, many of whom are atheists, many of whom are not Christians, and you meet them where they are, and you meet them with friendship and love. And then you can have a real discussion. That's where you find your shared humanity that goes across cultures, that goes across religions, is that shared humanity, because in fact, as we know, that's how God made us. He made all of us. He didn't just make Catholics, right? And so that's the place to start. It starts with love and humility and talking to people. And then you can have a real discussion. They'll ask you, like, well, why do you believe this, right? Instead of just saying you're stupid. That's not a conversation. So that's what I would encourage you to do. You can't do that with everybody. Not everybody's willing to engage in those kinds of conversations. And there are some true enemies out there. But for the most part, people are people. And you meet them with love and an open heart. And firm in your beliefs. And if they ask you a question you don't know, you say, well, I don't know. And you go off and try to ask somebody who does, or read a solid book that'll talk to you about this. And you come back to them. Don't make it up, actually. That's something you shouldn't do. Go and find out if you don't know. Yeah.
I just wanted to address, somebody mentioned something about intellectual laziness. I'm presuming you're being facetious when you would advise that we tell them that it's their pride, that simply because if we're taking the assumption that people are being intellectually honest, should there not be a greater responsibility to find a way to articulate clearly that there's intellectual laziness with regards to an inability to reason outside of an empirical box? Because that it's our responsibility as Christians to know that, to be able to say, as you said, science can't know itself. Well, what does that mean? To be able to explain it clearly. It's one thing to approach, if we can't at least explain that, then we're not doing our job as Christians, as far as, on the most basic level, because we may not be physicists and be able to explain X, Y, Z, but we should be able to have that explanation. And I find that there's if we are people of faith, I'm not presuming everyone here is a person of faith either. I think that's
Right.
something
I
maybe
think
may be
that's-
important to
I think that's
acknowledge.
true, yeah.
So if we're going to make the most charitable assumption about who's listening to us, then that they are believing this honestly, may not understand the limits of empirical reasoning, or reasoning that is absent of anything but empirical evidence. Should our responsibility not be greater as Christians to be able to explain that? And how can we improve that culturally to make sure that that happens? Because I think we should be able to do that.
I agree with you 100%, and that's certainly one thing I'm trying to do here and now in my new job and in my new sort of public ministry as a scientist. It's not really how I've been living my life until recently that I'll get up here and give a talk about this kind of stuff. I spent my career just talking about the science. But I think you're pointing out a failure of our educational system, at least in the United States. I can't speak to Canada, but even our Catholic high schools and universities are not preparing us to be able to answer these types of questions. And that's something that I'm trying to change. And it is up to us to try to learn this stuff, even if we're not going to go back to university to do so. There are a number of resources to start with, but I think it begins with these basic questions of, well, what does it mean? Why are we here? What are we for? That start that kind of conversation.
Thank you for your talk. So we learned from Catholic Church history that a lot of the greatest minds, like the scientists, were Christians or believers and bishops and all this stuff. So what happened about the break between faith and the science that now people are like promoting that kind of a division? And what can we do in the future to just bring it back?
I think I'd like to train a whole bunch of priests to become physicists, and I think we should certainly be training seminarians in seminary to give them a very solid foundation in the sciences, as well as the humanities, philosophy, and theology, but also the sciences, so they can go out and have a deep understanding of this type of beauty of creation, but also the science, be able to understand and speak coherently about the science itself. And vice versa, we need to prepare lay people who become scientists to have this connection between faith and science. And when I say that perhaps Catholic education has failed us, we haven't done a good job of making that connection even in our Catholic schools. And yeah, man, what you do is you crack open a history book and you say, oh yeah, Francis Bacon invented the scientific method. He's a believer. Georges Lemaitre discovered the Big Bang. He was a priest. Go on and on. Even Galileo, who gets a bad rap, he was a faithful man to the very end. So there's nothing that was incompatible with science and religion, even from the very beginning of the invention of science as a way to understand. And yeah, we kind of lost it along the way because we lost our way. We can get it back. Any other questions? Yeah. Okay, so we got two more questions and then that's it.
Hi, Professor. Thank you so much for coming today. I just wanted to ask, and I apologize to anyone who isn't a believer here, do you see atheism as an inherent danger to society in the long term? That's strong language, I know. And maybe secondly, if I can ask maybe a sort of side question. In terms of belief, I once heard that science sort of at its best gave evidence for agnosticism, not atheism at all, but would you refute that and say science, if you're a scientist and understand science well, gives evidence for theism?
I think atheism is a bad thing. I think it's harmful for people, and we should do our level best to meet them where they're at and to try to help them with that. But that being said, people have different points of view. We don't live in a theocracy where it's illegal to be an atheist, thanks be to God, nor do we live in a theocracy where it's illegal to be a Catholic. And so we have to have this type of freedom. And in fact, that's part of what's encoded into us is this freedom, in fact, to turn away from God. And that's what's happening there. And we read about it in the Bible, right? This is not a new invention. We read about people turning away from God from the very beginning. And so I think that's where that comes from. In terms of science leading people away from God, I think it's because we get a little too full of ourselves and think we're doing a good job. Science is amazing. I mean, look, science and technology are taking off faster than our culture is, taking off faster than our philosophy is, taking off faster than we are able to keep up with as people with relationships together, even with relationships to our planet. So it's extremely powerful, and it's easy to get kind of seduced into thinking that, yeah, because we're able to create these extremely powerful things, that's more powerful than these questions that I have in my heart, which in the end is God kind of knocking on the door.
It's okay. Hey, okay, so I understand that you have like separate philosophies of not comparing one thing to the other, like religion with science. But are you using religion to help your science to use this said a machine to understand, to unravel the beginnings of matter? Or are you trying to define what has made us, all of us, or are you trying to address the fact that you're able to do that?
Well, I'm thankful that I'm able to. I think that's the first thing, is just a sense of humility and being thankful for being able to do that, and having that be something that all of us actually are able to do because of who we are as people. Yeah, no, I mean, I try to go to Mass every day, and that's part of my job, in fact, and that helps me achieve a level of openness to the world around me. And if I don't have that kind of peace in my heart that comes from that experience with God, then I'm not as good a physicist as I am if I'm just caught up in my own anxieties. So that, in that sense, it helps me just as a person. But yeah, I do see the hand of God at work here in the world around me, and it's clearly an intelligible world. And I think it was Einstein who said the only thing that's unintelligible about the world is that it's intelligible. I mean, there's no good reason why the world should be intelligible, a priori. So for me, those two things, they're not incompatible. They're not sort of like parallel tracks. They're just like two things which are both true. Yeah.
To the fact of the matter, you know what I mean? Instead of the actual epistemological thought of what could have been opposed to what is. But I feel like because you have the fact, the evidence, and you're using this technology to define what is said, like what is here. But at the same time, like we have no idea what's out there. Do you know what I mean? But I mean, unless we have the technology to scan the rest of the, I guess the vastness of space, we only know what is here.
Yeah, no, I mean, scientifically, we, despite our all of these wonderful advances, we only know 5% of the energy content of the universe, and we've only recently discovered that we didn't know what 95% of it was. So if that doesn't expose a level of ignorance, then you're not paying attention. Yeah. Okay, thank you very much. Thank you all. Okay, thanks.
I'm just reminded of Tim Ingold, comments he made. He's an anthropologist from the University of Aberdeen, and as far as I know, not a Catholic, not a Christian, although I don't know. But he interesting comment at the opening. He was the keynote speaker for the opening of the social sciences building at the University of Ottawa several years ago. And he began by pointing out the following. He said that there's much that social scientists and scientists have to learn from both Anishinaabe, Ojibwe, shaman, and medieval monks. And the rest of his talk was really emphasizing the important distinction between a reductionist methodology, which is what has brought us this far in terms of science, and a reductionist epistemology. So just, very, I think, poignant remark by somebody who's not necessarily a believer. And I think just to emphasize, I mean, our audience here is certainly not just Catholics or believers. There are very honest agnostics and perhaps atheists in this audience, and it's very important, just as it's important to distinguish between, let's say, believing scientists with a great degree of integrity and searching for the truth and not afraid of what they might find through science, and those believers who might be very fundamentalist and fearful. We have to distinguish between, at the same time, atheists who are fundamentalist in their approach and those who are very honest and have a high degree of integrity. So just, I think others have hinted at that. I just wanted to make that very clear. And then invite Professor Paul Allen to say a few words about his organization, which has co-sponsored this event, and to thank our speaker. Thank you.
So just to end things off, so as Cecil mentioned, my name is Paul Allen, and I'm a professor of theology at Concordia University, known around here as the other university, 15 minutes to the west. But I'm wearing the hat tonight as a member of the Montreal chapter of the organization that you see on the slide in front of you. This is the Canadian Scientific and Christian Affiliation. This is an affiliation of scientists and those who are interested in science who are also Christian. And it's the Canadian affiliation, the CSCA, is affiliated with the American Scientific Affiliation, which is the same body comprised of the same sorts of folks in the United States. So someone asked the question a little while ago, where can I go to get some books and so forth? You can begin by looking up some of the titles that are mentioned in 2 leaflets that are on the table, literally as you leave tonight. As you're looking forward to that nice fresh air out the door, don't forget to pick up one or both of the leaflets that are in Christmas red and green downstairs, as well as a postcard that gives just the basic information about the CSCA. And the CSCA, as I mentioned, is an organization that of people, of Christians who are interested in science, whether scientists or those who are interested, like me, in science. So this is some places you can go on the internet to pick up information about the CSCA, and a couple of events, or one major conference coming up in May. This is particularly for those of you who are practicing scientists or graduate students in science. You are particularly encouraged. There is a very interesting and diverse program of events at this conference, which will take place in May at Trinity Western University in British Columbia. And one of the associated events will feature Catherine Hayhoe, who's a very well-known Canadian-born climate scientist. And Catherine is based in Texas now. She does all kinds of material on the internet, of course, in relation to her work as a Christian and as a climate scientist. She will be one of the featured speakers there. So it just remains for me to tonight, I was sitting here listening as someone who's currently teaching a course at Concordia in science and religion. And one of the things that's really important, Cecil mentioned at the outset tonight, the work of Peter Harrison. Peter Harrison, if you go online and look up his books, better yet, pick up one of his books, one of the, if not the leading historian of the dialogue between science and religion, with a focus on science and Christianity in the early modern period. So often, these science and religion discussions, they go on at a very abstract level. But I think, as Aaron has shown here for us this evening, this is no abstraction. Like what we heard this evening was not just physics, but we also heard about the physicist. Right? So we've got these 2 things, and this is very important with to pick up from a historical and not just a philosophical, but also historical focus on what is science and religion really. It's about human beings trying to figure things out. And one of the things I've really enjoyed about teaching this course this semester is picking up or feeding off of the curiosity of students who can see the problem with fundamentalism on either side, right? We have fundamentalists on the scientific side, and we have fundamentalists on the faith side. One of the beauties of focusing on the historical aspect is to pick up on the human and the complex and the complexities of Darwin's own view of God. There's been books written about that. And that's what I loved about tonight's presentation from Aaron, is the nuances of hearing about the physics, but you can't go just from the physics straight to God. There's never it's not a direct path. It's something much more beautiful than that. It's got to be meaningful, and that's something that I loved from Aaron's presentation tonight, was to hear about the awe and the wonder. This is what takes us from the physics to the physicist, and thence to God. So on behalf of this Montreal audience, we're really appreciating this break from the snow and the cold, and to help us get out of our heads and our cold and our misery. We appreciate your presentation very much this evening. Thanks.
So just a few points, and for those who wish to stay for the reception, we'll begin that shortly. Anybody interested in future events like this, if you sign up through Eventbrite, we will send you just one email asking if you want to be on an email list, and you can say yes or no. Or if you didn't sign up, there is a sign-up sheet at the back here. There's also a basket for free will offerings for those who want to contribute to the cost of holding events like this. And our next event coming up, just so you know, will be on human rights and freedom of conscience, and that's a panel discussion March 16th. It's still in planning, the details, but we have our keynote speaker, William Saunders, and we're going to look at sort of comparison of the Canadian and American situations on that. So let's enjoy a bit of a reception. Thank you for those of you who have stayed right through to the end. I know we went a little bit over time, but please stick around and enjoy a glass of wine. Thank you.